Today I'm looking at a common confusion in 120, 240 volt systems. We'll consider which of these is correct. Are these two windings, or two halves of V winding, in phase with each other, or are they out of phase by 180 degrees? In a couple minutes, we'll look at my demonstration board. We'll set it up both ways so we can see the effects, take some measurements, and by then you have a pretty good idea. But I'll still come back to the whiteboard to explain some of our findings and to make my own declaration. I often draw these systems this way, and we'll find that the theory works regardless which schematic I use. The main difference here is that I have one winding where at the center point a turn is pulled out a little bit, a lug put on it, and I can splice in a neutral. It's where I get the term center tapped from. Here I have two windings, like dual voltage windings, and as long as they're set up in series, I can bring a neutral into the center connection point. Now, in this scenario, could I set it up so the halves are either in phase or out of phase from each other? And I suppose I could. If when the coil is being manufactured, all the turns go in one direction all the way up, both sides would be in phase with each other. But if when they manufacture it, they turn them this direction on the lower half, and then at the center point, reverse the direction of the turns, you would end up with two halves that are 180 degrees out of phase from each other. I'm going to look at voltage too. If I put one lead at the bottom and measure up turn by turn by turn, should my voltage increase? And yeah, we remember from transformer theory, more turns, more voltage. So if I have the same number of turns here as I have here, I should be able to get 120 volts here, 120 here, and then I want to get 240 from hot to hot, or 240 volts across the full winding. Also, notice something when I do the demonstration, how I orient my leads. If I put them like this and move them both up, or if I use the black lead in the center and the red to measure the voltage on the hots. It's as if I lived on a nice little river. And this section between my house and school, do I go with the current or against the current here? And it makes a difference. If my reference or my starting point is school, then I'm going against the current on this section. But if my reference is home, I go with the current on this section. We'll find that the orientation of the leads may have something to do with one sine wave being flipped relative to the other one. So which of these is a better representation of what we might see on a scope? Or could they both be, depending on how the leads are oriented? One last thing I want to do before we go to the board is, since I'm going to be using batteries, I want us to recognize that DC batteries can be used to simulate two sources that are either in phase with each other, working together, or 180 degrees opposing each other. Now, AC, yes, is always switching its positive-negative orientation, its polarity, if you will. But we can still use the batteries because we often analyze AC circuits at one moment in time. And the point I'm trying to make is that if the two are in phase, then they'll always be in phase, even as the AC cycles back and forward. And if they're out of phase, as the AC cycles, they will always oppose each other. With my 3-wire single-phase mock-up here, you can see that I have two sources, or two halves, that are in phase with each other because the copper tops are all pointing the same way, and the loads seem to be working fine. Now I'll turn this half around so that the two sources, or two halves of the source, are out of phase from each other by 180 degrees. What we find is our line to neutral loads seem to be working fine, but I lost my line to line. We'll start by measuring some voltage. And sure enough, line to line, practically nothing, about 0.005. So there's obviously voltage here and here. So let's start at our source. As I start here, 1.2 something, increasing cells, the voltage should increase, very similar to more turns of a transformer secondary winding. More turns, more voltage. So the voltage will keep building as I move my way along. And about 3.5 volts at the center point. But then if I keep going, the voltage starts dropping because of the opposing polarity of these cells compared to the first half, 180 degrees out of phase. So by the time I get to the red wire, there's no voltage left. Because the two banks are opposing each other, the voltages cancel each other out on the line-to-line measurements. Let's measure current as well, because that can be a problem with this out-of-phase setup. Here on the black wire, I have about 8.5 amps. Now, it doesn't take 8.5 amps to run these little lights, but I have 10 loops here that magnify the amperage by a factor of 10. I also have 10 here and 10 here, so we're still measuring apples to apples. The other thing to notice is that it's positive, as I'm measuring with electron flow in mind. Electrons flowing from the negative end of the battery around to the positive. Whereas our friends in the academic world, they measure with conventional flow, which has its merits, and we use it sometimes, but we'll leave that friendly discussion for another day. Anyway, I've got about 8.5 amps flowing out to the loads. And if I measure the red, well, I've got 8.5 amps, and it's also positive in this out-of-phase setup. So it's going out to the load as well. How about the neutral? Ooh, here we've got 17, and it's negative, little over. It appears that the neutral is bringing back all the current, rather than just the unbalanced. And since we have a balanced load, there should be no amperage on this section of the neutral going back to the source. Rather, the current from one side should be continuing through the other loads and making a big circle like this. But the sides are opposing, they're not working together. What's happening here instead is that each half is pushing out and forcing the neutral to do double duty, creating a scenario where the neutral is carrying the addition of the currents from each side rather than the difference. Let's go back to the in-phase setup to see what voltage and current measure here. Let's look at voltage on the in-phase setup. And sure enough, it keeps adding on the same side as we add more cells. But here in the in-phase setup, when I cross the center point, it keeps increasing. And so we end up with black to red voltage being about 6.3, 6.4 volts. And since we have 6.3 volts here, we should expect about half that from black to white. Sure, 3.1, 3.2. And from white to red. Again, 3.1, close to 3.2. Did you notice, though, the orientation of my leads? I measured both my leads in the both halves in the same orientation as the source. So when I measured from black to white, that equated to going from negative to positive, and from white to red, from negative to positive. So they both read positive 3.1 or 3.2. But if I put my black lead in the neutral and measure both hots with my red, one will read negative and the other positive. This shows that from the perspective of the neutral, the black wire is negative. Reference going from the positive end of the batteries to the negative. It appears negative. But keeping the reference on the neutral, the red wire appears positive, and indeed is positive because it's going from negative to positive. So the two appear to be opposite from each other, but it's really a matter of polarity. I'm measuring from the middle of my batteries, looking down to the negative side on one point, and looking up to the positive side on the other. I'll relate this voltage reference concept back in the whiteboard where I had the sine waves. But first, let's look at current on this in-phase setup. Okay, here I've got about 13 amps and it's positive. So that's flowing out to the field. A little higher amperage because now my line-to-line load is working, drawing extra amps. So 13 amps going out to the field. And on the red wire, 13 amps, a hair more, coming back in. So now we're working in that big circle that we were talking about earlier. What should I have on the neutral? Sure enough, balanced loads, practically nothing, 0.02 amps on the neutral. The only time the neutral should be carrying a current is when we are, at least on this portion back to the source, is if we are unbalanced. So here, this side is heavier and it's a positive 2.5 amps, but when this side is heavier, it will be a negative. And that's because at this moment in time, AC is always flipping back and forward, but at this frozen moment in time, when the current is flowing this direction, it's flowing this way through the line to line, this way through the balanced portion, but the unbalanced portion uses the neutral and still flows through the source in the same way. So it's coming back the neutral negative. If I switch it over and the heavier load is on the red, sure, still the balanced part is going all the way through in a big circle, but the unbalanced portion is just using this half and it's going out the neutral, therefore the positive, and coming back the red. There were two major problems when the two halves or two windings were 180 degrees out of phase. The first is that the line-to-line loads didn't work because the opposing voltages canceled each other out. And the second was that although the line to neutral loads worked, they were set up in a way that caused the neutral to carry all the current back to the source rather than just the unbalanced. And this could easily overload the neutral. My declaration, therefore, is that in order to have a 120, 240 volt system to operate correctly, the two halves or two windings must be in phase with each other. And that means that for this winding here, the turns have to be wound in the same direction all the way up. Earlier I mentioned the term center tapped, referring to this neutral connection. But there's another phrase that can help us with these systems, split phase. It can help to think of this as a single phase winding with 240 volts induced into it. But how about my 120 volts? Well, in the same way that more turns equals more voltage, fewer turns equals less voltage. So voila, split phase. Split the single phase winding into two parts. Now I have 120 volts here, 120 here, and all the while I have maintained my 240 across the whole thing. Last thing I want to do is make sense of these sine waves. And a meter like this is not going to read polarity or negative positive on AC, changing back and forward too quickly. But a scope can capture an image over time and compare different connections to each other. So I'll use this black, just in my illustrations here, as my reference point, and the red will be what I'm measuring. So this is the reference. And the first picture is using a common reference point, the neutral. So one wire appears negative, the other appears positive from the point of view of the reference. It's like my river here. If home is my reference, I'm going upstream to the shop and downstream to school. But all the while, we know the river has to be flowing in the same direction all the way. So when I have my reference on the neutral, one goes down against the arrow, reads negative, the other positive. And in AC, these will flip back and forward, But at this moment in time, we're kind of in the first half of either of these sine waves. Now, if I want to measure from black to red with this first drawing, I could imagine flattening out the black line to make it my reference, and then moving the neutral and the red accordingly. Since the black wire is now my reference, I'm measuring from here up to the red. And so we've got a full 240 volt sine wave, twice as tall as this one. And because the neutral is right in the middle, halfway up, its sine wave is only going to reach halfway. This is using black as the reference. If we wanted to flatten that and see how the black compares to the red, push these up, because the distance here and here will remain the same. It's just they not both now appear positive because we're going in the positive direction for both of them. Now over in this drawing, you'll notice I have the black and the red right next to each other. And here, we're actually using different references for each of them. We're measuring the coils like this, but we are measuring them in the same direction, from bottom to top, bottom to top. It's like going over to my drawing here. I'm starting at the shop now, going downstream to home, picking them up, or in the case of a scope, having a second set of leads, going from where I left off down to school, downstream both ways. And if I have two coils here that are both in phase and the same voltage magnitude, if I put them in series, they'll double my voltage. So which of these two, if my system is set up correctly with the two coils in phase, should I be able to see on a scope? Both. But the key to understanding how both images could be seen on a scope is knowing what reference is being used. The red coil here is measured the same way in both images, from neutral to red. Neutral to red and neutral to red. But the black coil, that's where the subtlety is. In the first picture here, it's measured from neutral down to the black wire. But in the second picture, the orientation of the leads is changed and it's measured from black up to the neutral. It's that change in the orientation of the leads that flips the black sine wave relative to the red one. And there you have it. My attempt at explaining why the two halves of a 120, 240 volt single phase system are in phase with each other. Thank you.